Hi, so thanks a lot. So thank you for the invitation. And again, I'm sorry I could not come in person this time. This is going to be about a joint work with a former postdoc of mine, so Giorgio Stefani. So it's currently at SISSA in Trieste. And this is about a new, say, elementary approach to a well-known problem, which is that of uniqueness for the Euler flow in the so-called Yudovich spaces that we shall see inside the talk. They are sort of spaces in which the vorticity is quite close in integrability to being L infinity. So I'll be more precise in the following. So a very short introduction, which is, well, maybe not so needed for this audience. So the Euler equations have this form. So there is no viscosity. So V is the velocity, P is the pressure. So, and we are assuming, or the equations prescribe that the divergence is equal to 0. The 2D case is very special in that we can define a vorticity, which we can always do, but into the special strong properties that this is scalar, or it may be identified to a scalar. So omega is the curl of the velocity V. And then what you get is that the vorticity is just advected by the velocity, so there is no stretching, which is the strong difference in contrast to the three-dimensional case. But again, so you're not just removing all difficulties. So the equation moves from a nonlinear equation to a non-local equation. So V is not given, is not prescribed, is reconstructed by the vorticity via the so-called Biot-Savart law. Okay, so as a convolution operator. And now something, okay. So we shall focus on uniqueness and non-uniqueness under assumptions on the vorticity. So in particular, let me recall, so what are the most important results? So concerning uniqueness, so Yudovich showed uniqueness for bounded solutions or solutions with some mild growth of the LP norm, while Vichik extended in a sense that to BMO-like vorticities, and the proof becomes much trickier, also because he needed more conditions for the existence. So he could prove uniqueness but not existence, or not persistence of the BMO norm. And this opened the way for many other interesting works, starting by Bernico and several collaborators. So on the other hand, so it's becoming more and more apparent that uniqueness does not hold for LP vorticities if P is strictly less than infinity. So there are many interesting works which appeared in the last couple of years. So Vichik showed that for LP vorticities for any P less than infinity, but paying a forcing in the equation. So Alberto Bressan and some collaborators, they had a sort of computer-assisted proof in a sense. So they identified a configuration which should lead to non-uniqueness, but some steps in the proof, they are not yet analytical in a sense. And also quite recently via convex integration, Elia Bru and Maria Colombo. So I think Maria presented this result in the second workshop inside this period at Cambridge. So they showed the non-uniqueness in weak Lebesgue spaces, so spaces of the type L1 infinity, which is strictly less than L1. So it's a larger class of vorticities. Okay, so how does the Yudovich proof work? So basically it is based on an estimate for the relative energy. So we consider two solutions. We consider the L2 distance between them, so the square of the L2 distance, and then we try to do an energy estimate on it. So I have a bit of a problem with my Acrobat, in fact, so it's quite slow. I hope you are seeing that correctly. I'm not all the time. So as I was saying, so you consider two solutions, V1, V2, and then you do, say, the standard energy estimate for the difference of the two solutions, and then you get the following, so this differential inequality. So the time derivative of this relative kinetic energy is estimated by grad of V1 times V1 minus V2 squared. So if we had that the gradient of V1 is bounded, then we could just conclude immediately by using the Cromwell inequality. However, the gradient of V is given by a Calderon-Zygmund singular integral operator applied to the vorticity. And these singular integrals, they are not well behaved on infinity. So you can just estimate the norms in LP for every p less than infinity, but not for p equal to infinity. And in particular, if you track the constant, you see that the constant grows like p. Okay, so you would have a trivial estimate for p equal to infinity. This also reflects in the fact that you don't have a Lipschitz regularity of the velocity, so you only have this log Lipschitz regularity, so you have a sort of a loss in it. Okay, seems my Acrobat is stuck. Okay, so what is the trickery in a certain sense? So how could Yudovich solve the L infinity case? We were in the previous slide at this point. So you estimate in the following way. So you put LP on the gradient of V of the velocity, and you put some L infinity and some LP prime, where P prime is the Holder dual, on V1 minus V2 squared, leading to the following. So I have a piece which I just estimate here in L infinity, because I know if P is greater than 2, my velocity is R in L infinity. Here I have this LP prime norm of this power of the difference of the velocity, and here I'm bounding this with C times P, thanks to Calderon-Zygmund. And then all in all, I arrive to this inequality. Okay, so I get a differential inequality for the relative energy. However, we cannot use ground wall at fixed P because the right-hand side has power strictly less than 1. Okay, so it does not give uniqueness at fixed P. Okay, I think I'll just pass to the other. So I have a problem here. Let me go back to the preview, which seems to be a little. Okay, I think I was at this level here. Okay, so as I was saying, so this is not fine for fixed P, but we can play the following trick. So we can write for a general P the maximal solution, and then we see that for short times, so if we look to a time horizon t less than 1/2 times c, we can just consider the maximal solution and then let P go to infinity in the maximal solution. So we get local in time uniqueness. So this is Yudovich's original proof for the case of L infinity vorticities. Let me show what I mean for mild growth of the LP norms of the vorticity. So let us assume that we consider vorticities for which the LP norm is some function theta of P, of the exponent, and we will see what we mean by mild growth. So we can play a game which is very similar to what I was doing right before. So we can estimate the time derivative. I can do an energy estimate, the time derivative of the relative energy. I estimate in the following way. So for a fixed parameter epsilon, I put a gradient of V1 in L1/epsilon, a part again in L infinity, and the part in the dual holder, so L1/1 minus epsilon. I get the following. And then I use my assumption that the vorticity in LP is growing like theta of P. And then all in all, I get the following expression, which I also rearrange a little bit. Okay, now I give a definition. So I define a function psi theta of the variable, whatever, zeta, which is just this function here. Basically, I am optimizing my right-hand side as a function of epsilon. And then I get the following. I get that the derivative of the relative energy is estimated by sort of a Lipschitz part, so a ground wall, a part which is defined from ground wall, times this function psi theta of 1/the relative kinetic energy. Then we can conclude uniqueness under the Osgood assumption. So if this right-hand side has Osgood regularity, then we can conclude uniqueness for the Euler equation. So this is quite nice, still quite implicit if we remain at this level. So there are a couple of canonical examples in which we can really write down the function psi theta. So if omega is a logarithmic singularity, then it's easy to see that the LP norms grow linearly in P, and then this function psi theta grows like, or degenerates like a log, which is non-Osgood, so we cannot conclude uniqueness. On the other hand, if the singularity of the vorticity, blow up of the vorticity is like a double log, then the function theta grows like log, and then we get a log-log for the function psi, and then we have an Osgood condition, okay? So this is why, in a certain sense, Yudovich proof could not apply to BMO singularities, okay? So to BMO vorticities, because log is the typical BMO singularity, and that's why Vishik's paper was then needed in order to tackle this case. So let me make two remarks, which are functional to what I will say later. So Yudovich's proofs, so it's quite cute, but it makes an essential use of Calderon-Zygmund theory in that it really uses the sharp constants or constants in Calderon-Zygmund inequalities. Second, the condition on the function psi defined as this inf is sort of implicit, okay? So we have the growth of the vorticities, then we define some inf, and then we ask that this function defined through this infimization process satisfies some Grunwald condition. Okay, so in this work with Giorgio, so we do the following. So we give an alternative approach to this Yudovich's proof, which first does not use Calderon-Zygmund at all. So it's much more elementary. In fact, as we shall see later, we don't even use Sobolev spaces in our proof. So that's a tool which is completely avoided. And in a sense, we shall see that. So we use a sort of more metric approach, and we will have a Lagrangian, in spirit at least, proof of the uniqueness. Another benefit, so if the first one is maybe more, say, an aesthetic approach and an aesthetic advantage, the second one is that the uniqueness conditions on the function theta, so on the growth of the vorticity, they become much more explicit. Another benefit is we can treat also the so-called uniformly localized Yudovich spaces, which one defines in the following way. So you remember that so we were prescribing earlier some growth condition on the LP norms of the vorticity. We can work in spaces in which we just prescribe a control on the growth of the LP uniformly localized norm of the vorticities, where these LP uniformly localized norms are the following. So the maximal norm in LP of the function, the vorticity in our case, on unit balls, okay? And the main lemma, so which makes everything very explicit, is an estimate for the modulus of continuity for the velocity under the assumption that the vorticity is in this uniformly localized Yudovich spaces. Okay, so we can show that the velocity is phi theta continuous, where phi theta is this function here. Okay, focus. So just to understand what I'm saying more precisely. So if the vorticity were bounded, the LP norms would be uniformly bounded in P, and then this function theta would be constant, so we would not have this last term here, and then we would recover log Lipschitz continuity for the velocity. Here it's basically a generalization of that. So we can have mild growth, so this function theta can go to infinity, and then we have a more irregular, so a more general sort of corrected log Lipschitz continuity for the velocity. Okay, so this is the remark which I was just doing. So if omega is bounded, then the velocity, so we recover the classical log Lipschitz. Similar computations for the Vlasov-Poisson equations have been done by Evelyn Mion a few years ago. However, in her paper, she remarks that the type of computation, in the way at least she does, they don't extend to the case of the Euler equation, so they are not suitable to prove uniqueness for the Euler equation. So in this sense, we have some differences compared to her approach. And as I was mentioning, so the sort of metric approach. So we don't really need the differential structure. So we just need the fact that we have some vorticity which is transported, and the velocity is recovered by the vorticity via some integral convolution operator of this type. So v at x equals the integral of kxy omega y dy, where we assume two conditions on this kernel k, which are satisfied for the Biot-Savart kernel in R2 or in a nice domain or on the torus. So the first one is the decay. So at the singularity, there is a blow up like 1 over the distance to the singularity, so which is the first condition here. The second one is what I call it oscillation, or is a sort of Lipschitz regularity of the kernel away from the singularity. Okay, so if I look at the dependence in the first entry for this k, so it's Lipschitz, but of course there is a degeneracy when I go to the singularity. Okay, so the kernel is not Lipschitz, of course. We don't really have assumptions on the domain directly in the following sense. So everything is now put on the assumptions on the kernel. Okay. So if you look at if k basically is a rotated gradient of the green function, the regularity you need on the domain is basically the regularity that you need in order to have a kernel. So a rotated gradient of a green function, which satisfies those two properties, so decay and oscillation. So this becomes sort of implicit. If you prefer, just think to the case of R2, okay? And we can also, but I will not insist on that, relax the incompressibility assumption within this approach, which is not very interesting in the context of fluid dynamics. But the proof is sort of flexible. That's the message I want to convey. And the other message I want to convey, so the computation is super simple in a certain sense and direct. So I want to show an estimate for the modulus of continuity for the velocity. Okay, I pick 2 points in my domain omega, and I call d their distance. I assume the distance is less than 1. Okay, I split v of x minus v of y, which is k omega x minus k omega of y. So it is expressed by this integral. I estimate, I put the modulus inside, and I split the integral, as you would expect, in 3 different regions. So close to x, far away from x, and at a sort of intermediate distance, so comparable to the distance between the 2 points. And then I estimate separately the 3 terms that I get. So I use far away oscillations, and I get just some Lipschitz term, so no big surprise there. On the intermediate scale, I use again oscillation, so I get a sort of Lipschitz piece, but I have now something singular here, which I will treat in the next slide. Some sort of energy, if you want, of the vorticity. So here it's quadratic at the denominator, and I am in this intermediate regime here. Very close to the point x, I use decay, and then I get, so I don't have a Lipschitz term in front here, but I get two terms, which I will add up, which are similar, one with the other, and they are just linear here in the denominator. Okay, so second step in our main computation. So we need to control these 2 functions that I have here at the right-hand side. Here I have this Lipschitz part times quadratic, and here I have linear in the denominator. Okay, I need to control them uniformly in the point around which the ball is centered. And then I do the following. So again, it's a super simple Holder computation plus an explicit integration. Okay, so there is nothing more than that. And here is the place where you see that naturally, so these uniformly localized norms show up. So for the first term, we get a d to the minus 2 over p behavior. Remember, so d is the distance between the 2 points, x and y. And for the second one, we get d to the 1 minus 2 over p. Okay. So in the end, it's the same thing, because you remember that for the first term, I already had the Lipschitz thing in front. Okay. Then, all in all, we got the following statement about the Euler continuity. So if the vorticity is in L1 global, cap LP uniformly localized, where P is greater than 2, then K omega is Holder, so the velocity is Holder with an Holder exponent 1 minus 2 over P, with explicit estimates, okay? And the fact that these estimates are also explicit in P is going to become important in the next slide. So be careful. So this should not come as a surprise, since for the Biot-Savart kernel, so you just applied Calderon-Zygmund and then Mori inequality, and then you get exactly this Euler continuity, okay? The message is more that the proof is elementary, is completely in real variable, and does not make use of any other tool. Okay, so how do we move from the Holder to the continuity, to the phi theta continuity, when the vorticity is in this uniformly localized class? So we arrive to this formula here, and then we just rewrite it. So now my vorticity omega in LP uniformly localized is bounded by theta of P times the uniformly localized Yudovich norm. And then I just choose P. So I have this estimate for every P less than infinity. I have 2 points, X and Y. And then I simply pick P equal to 1 minus the log of this distance. And then I get exactly the formula that I wanted. So here is theta of P, theta of 1 minus the log. So now the P here becomes the log factor. I have the Lipschitz part, so X minus Y to the 1. And here I have the magic computation that number times minus 1 over the log of the number is uniformly bounded, okay? And then I get exactly what I stated at the very beginning. So this is the main computation. So this explicit quantitative a priori estimate on the modulus of continuity of the velocity for vorticities which are in Yudovich theta uniformly localized. So let me stress one thing. So until now, we had no conditions. So I was advertising at the beginning for this mild growth. So until now, there are no conditions on the growth functions, theta, until now, which reflect, is a thing which reflects in the fact that, yeah, I'm calling this phi theta a modulus of continuity. Well, does not need to vanish for the zero increment. So it does not hold in general that phi theta of 0 equals to 0, and that phi of theta is continuous at the origin. Okay, so if you assume nothing on theta, you don't get the continuity of the velocity. So you should not get it. Okay, so it's completely correct. I still, with a small abuse of terminology, call it modulus of continuity. Very nice. So using this, we can prove under certain assumptions existence of solutions, of weak solutions, under some more restrictive assumptions, in the spirit of Yudovich result, uniqueness of the solution. So for the existence, so we can offer 2 results. So if the initial vorticity is in L1 globally and LP uniformly localized, P greater than 2, we can prove existence of solutions which maintain locally uniformly in time the same condition on the vorticity, and the velocity will be Holder continuous with this exponent. Moreover, so if the initial vorticity is also in Yudovich uniformly localized, then we have a solution which stays in Yudovich uniformly localized, and the velocity has this continuity property. Again, no conditions on the growth function up to now. If phi theta is Osgood, which boils down to some conditions on theta implicitly, then the weak solution is also Lagrangian. Okay, so the unique flow of the equation, so unique because it's a flow of the of an Osgood velocity, also transports the vorticity. So you have this bonus physical property in a sense. And this has to be compared to results by Tanucci, so some 15 to 20 years ago, in which it was doing comparable results. So it was not assuming global integrability. On the other hand, the method was quite different. So it was more paradifferential calculus, and it was working in the full plane. Okay. So I just give a couple of words about the way we prove existence. And here, well, depends, you know, a little bit on your religion in a certain sense. So I was advertising before for this sort of metric proof. We don't really need this differential precise structure of the Euler equations. Okay, it does not need to be the Biot-Savart kernel. On the other hand, so if it's not the Biot-Savart kernel, then we don't have an equation for the velocity in general. And then we cannot rely on the theory of existence of smooth solutions in order to then do some truncation, some regularization, and show existence of weak solutions. So you can take then two approaches. So either for the existence, you just look at the Euler equation, and then you're allowed to use that, or you reprove everything from scratch, which is also, you know, something that that's. Entschuldigung, sorry. There was a question? No.
No, there's no question.
Okay, thanks. And then, okay, we implement this other strategy, okay? So we wanted to keep our proof completely, say, metric in a sense. And then we redid via some time-stepping arguments, the proof of existence in L1 capital infinity, okay? So time-stepping was, you know, the suitable way that we found in order to do this at our level of generality. And then by truncation, we constructed a solution in L1 cap LP uniformly localized, and then we had to show propagation of this LP UL and Y theta UL for the vorticity. And here one technical tool is some version of the Aubin-Lyon lemma with weak compactness in space. So Aubin-Lyon typically allows you to gain strong compactness in time because you have an equation for you typically use that at the level of the velocity. Yeah, you don't have to, but if you use that at the level of the velocity, then you have strong compactness for the velocity, and then you also upgrade the weak compactness in time to strong compactness in time. We don't do that. We use that more at the level of the vorticity equation, and then it's a variant of the Aubin-Lyon lemma with weak compactness in space for the vorticity. That's a minor variation. So what's probably more interesting is the uniqueness result, which we can prove under the following assumptions. So assume that theta, so the growth of the LP norm of the vorticity, is so that the modulus of continuity phi theta is concave and Osgood. Okay, so this amounts to a certain relatively explicit control on the growth at infinity of theta. Okay, if you look at typical examples, we are not really improving Yudovich. Okay, so if you look at basically concatenation of logs, we are at the same scale. We just, in a certain sense, polish and make more explicit the condition. So we assume phi theta is concave and Osgood. Then there is a most, and then here I have brackets, so one Lagrangian weak solution, such that it belongs locally uniformly in time in this class, and for which the velocity also is in the corresponding continuity class, starting from an initial datum in the same class. So we recover and improve / polish Yudovich. So the proof is, as I was mentioning right at the beginning, is sort of a Lagrangian in character, and now I will explain this parenthesis around Lagrangian. This is more, so it's less in the spirit of Yudovich relative energy proof, it's more in the spirit of, say, Serfati-Lepere proofs, and also of the proof that you find like in the book by Marchioro and Pulvirenti. Okay, so it's a Lagrangian proof. And then, okay, so there is this Lagrangian in parentheses. So again, you choose your religion. So if you don't want to use any big tool and stay completely self-contained and elementary, so we just prove uniqueness of Lagrangian solutions. You may wonder whether it's true that every weak solution of a transport equation with an Osgood velocity field is Lagrangian. So the answer is yes, that's true. So the class of weak solutions and the class of Lagrangian solutions coincide, but it's not a trivial thing, okay? Because you're dealing with weak solutions, okay? Of course, you have a unique flow, but you don't know if a weak solution is transported by that pointwise unique flow. But this has been proven in very different ways. So by Ambrose and Bernard, I think more like currents-like argument, and then by Klopp and collaborators, more harmonic analysis proof, and that's also a spin-off of something I was doing a couple of years ago with Laura Caravenna, with some sort of more real analysis approach in a certain sense that we develop for other reasons. So what is a Lagrangian proof? So how do we deal? So in a certain sense, you will recognize, if you're familiar with these tools, a sort of Wasserstein distance approach. Okay, so you give me two solutions, two vorticities. I assume they are Lagrangian, so there are two flows for them. The solution is represented by the push forward of the initial datum via those two flows. Okay, I fix a time horizon, capital T, and then I estimate the difference of the two flows. So I don't prove directly uniqueness of the vorticities, I prove uniqueness of the flows. I use the ODE, and then I write the flow as integral of the derivative of the flow, and the derivative of the flow is the velocity computed along the flow. Okay, so that's this first line here. And then I do this triangular inequality thing. So I insert, so I add and subtract V1 along X2, okay? And then for the first term, we very simply use the phi theta continuity, okay? So V1 as an estimate in terms of this phi theta continuity, okay? And the first term is easy. The second one is more like a stability term, okay? So I need to estimate the difference of the two velocities, but they are at the same point. And here the trick is I reintegrate in space, basically, okay? So I have this V1 minus V2 at X2. Then I write the velocities as K of omega1 of omega2. Then I have this other integration. And then I get at the end of the day an estimate of this type. So K of X2 at 1 minus K of X2 at X, X2 at Y, and I integrate in the Y. Then we combine the two estimates. As I was saying, we then integrate everything, and then we go to the following slide. So here there is one technical thing which is not really important. So if you're dealing with an unbounded set, you have a technical thing that you need this function eta, which is just a fixed function, which is L1 cap L infinity, strictly positive on the entire domain. Okay, just forget it if you don't like it. So basically, you are just integrating the estimates that I had here on the right-hand side, okay, on the domain omega, okay? And then at that point, we can start applying Fubini, so swapping the integration in Y with respect to Lebesgue, and in X with respect to basically the total variation of the initial datum, so the absolute value of the initial datum. You do that, and then you use a variant of the estimate that I presented you with a lot of details in the first half of the talk for the modulus of continuity. So here I have basically something which is like K at X1, X2, and then I am integrating in this push forward of the vorticity. So this is an estimate which is very similar to the estimate for the modulus of continuity of the integral operator applied to the vorticity. And then I get the following. So I get the integral of omega 0 at y against the modulus of continuity applied to the difference of the two flows, which again is expressed in this way if I change variable back again. So if I use the fact that I define omega mu in this way. Okay. Okay, in conclusion, so you put together all these computations. So from here, I was already estimating the difference between the two flows with phi theta. And also the second term after integration, I processed in the same way. And then all in all, I get that after integration, I get a time integral of a space integral of this phi theta of the difference of the two flows. Since phi theta is concave, so first assumption we are assuming we can apply Young inequality. Okay, and you find that this is bounded by phi theta of this integral of the difference between the two flows. But then, being phi theta Osgood, the second assumption that we have on our modulus of continuity coming from suitable conditions on the growth function, we if we define this psi of S to be the difference between the two flows at the time S, we get a differential inequality of this type, or I mean, this is in integral form. Psi of t is controlled by the integral in time of phi theta of psi of S in the S. And since we are assuming an Osgood condition on phi theta, we get that the two flows coincide for every t between 0 and capital T, which was arbitrary. And then from this, it follows that the vorticities coincide, and then also the velocities coincide, which is the uniqueness results which I wanted to prove. And that's all from my side. Thanks a lot for your attention, and I am looking forward to the questions.
Thank you, Gianluca. Thank you for the acrobatics. From any questions? Oh,
Hi, Gianluca. Very nice talk.
Hey.
So I understand, of course, from your proof that you need the vorticity to be in L1, but I wonder if there is a way to modify a little bit this approach to allow vorticities to decay slower at infinity.
Yeah, we are doing that. So in fact, the right setup that we can probably deal with is like the Serfati one.
Okay.
So you just don't assume anything global on the vorticity. You assume the velocities in L infinity.
Okay.
So
okay.
this can be most likely. So we are checking that now.
Okay, great. Thanks.
There's a question in the chat. Go ahead.
Yeah, I have a question. Thank you for a very beautiful talk. I really enjoyed it. So I just had a question about, you may have mentioned something about this, but Yudovich allows for prescribed circulation on like a multiply connected boundary, right, with like holes in the domain. I feel like this approach should also allow that. Is that right? Does that seem right? Or? Yes, I feel like it should go.
Yeah, I think so. So in a sense, our approach really puts everything on the Biot-Savart kernel. So once you have that, you don't really see about circulations. Yeah, so I would guess yes.
Okay. Yeah.
So this comes implicitly in a sense.
Thanks. Yeah, that's kind of what I was thinking. So yeah, very beautiful. Thank you very much. It's great.
Thank you. Any
other questions? Well, I think everybody's ready for lunch here. Thank you very much, Gianluca.
Thank you. I just stopped sharing. Great. So thanks a lot, everybody.
Thank you.
Thank you. Bye.